In this video, we're going to discuss analysis of variance. First, I would like to set up the data set we will review. This is an ortho-K data set in which two lenses were tested. One was a spherical base curve, and it had a 6mm optical zone design. And the other lens was aspheric base curve, and it had a smaller 5.4mm optical zone design. And then I'm not going to go into the details of what we did, but I would like to just explain three groups that we're going to talk about. Because this is analysis of variance, we want to have more than two. So I split out the spherical group because it was in that case the lenses really looked like they were two different groups of people. This graph we have baseline axial length, and we have axial length over 5 years. All the subjects were followed for 5 years. And axial length was measured each year. And we had an aspheric design. Now this black line right here is a line of identity, which means that if your axial length was 25 millimeters at baseline, then a point on the line is 25 millimeters at 5-year follow-up. So if there was absolutely no growth of axial length, you would be up here. Now the open circles are the aspheric lenses. And pretty much you can see that across the entire baseline, they didn't grow very much. And then, so this dotted line actually is 2 standard deviations above the mean regression line for the aspheric curve. And then dots that, or subjects that fell that grew more than outside 2 standard deviations of normal are represented by these triangles for the spherical design, and the little black dots are spherical designs that fell within the 2 standard deviation criteria. So we have 3 groups: 2 spherical OZ designs, one that fit well, or one that had less growth, and one that had more growth, and the aspheric design. So that's the data. Now, what we did was we defined a lens type as spherical or aspherical. Then we have the second definition where we have spherical works well, spherical doesn't work, and then we have aspheric. Both eyes were measured, so we have a left and a right eye. At baseline, we looked at age, spherical, sphere, cylinder, axis, the horizontal keratometry, the vertical keratometry, and the axis, the eccentricity, the pupil size, the central corneal thickness, and I don't know what happened to HVID. Did I miss that one? Oh dear, must have deleted it somewhere. Okay, so then we have axial length at baseline, 1st year follow-up, 2nd, 3rd, 4th, and 5th, and then the change at 5 from baseline. Now we matched these subjects on using a propensity analysis. We're not going to go into the details today. So when we do an analysis, of course, the first thing we have to do is test our assumptions for analysis of variance. Are all observations independent? Are they are the distributions normal? And is their homogeneity of variance between groups. So in order to do this, what we're going to do is we're going to split the file by I. First of all, we have to do, in this case, if the left and right eyes are not independent across subjects. So we need to, if we're going to run this analysis, we have to run it separately in this particular format, just a simple one-way analysis of variance. We're going to have to split the file between left and right eyes so that we don't get into that dependence. And for measuring normality and other things, we're going to split by group. So we check out normality by individual group. So that's going to be lens type. Okay, now we have split the file. And then let's look at whether or not they're normal. So let's look at the variables we have. We're going to just include axial length at baseline at 5 years. It's a normal test distribution. Okay. Now remember, in the QQ plot, we want to see straight lines between the baseline measure and the y-axis. So let's see what happens here. Okay, this is sphere. That looks not too bad. Cylinder, not too bad. X, what's this? Oh wait, this is the left eye lens type 2. Spherical, works well. So that's this one. This is left eye spherical, doesn't work. This is aspheric. It's kind of a little wavy. This is the right eye. Now we're looking to skew to the left a little bit. And again, kind of wavy, but sort of in the neighborhood. And this is spherical again. Left eye spherical doesn't work. Left eye aspheric, ugh, we're starting to get a little bit of a deviation from normal. Is there anybody that's... Now, one thing that we have to keep in mind here is while these guys, some of them don't follow normality too well, our actual test today is going to be on axial length. So let's go find that. We did a lot of QQ plots here. Here we have, this is let's go to baseline. This is axial length at baseline. And this is the spherical works well. Spherical doesn't work well, a little skewed. Aspheric, also a little skewed to the right. Not too bad though. This is the right eye. Doesn't work well. And aspheric. So it looks like the doesn't work well is a little bit skewed to the right. This is the axial length at 5 years, not too bad. This is the left eye. That looks okay. Doesn't work well, it's not so bad after 5 years. That's a spheric, not too bad. Here is the right eye. Looks pretty good. Doesn't work well. Looks pretty good. Aspheric. A bit of a tail down here, but not too bad. Okay, so for our question for today, looking at the, just as we test if there's a difference of between the axial length after 5 years, it doesn't look too bad. It's reasonable enough, let's say. Now let's go to how we would do this. We're going to go to compare means, a one-way ANOVA. And there's a couple ways we can do this test. This is one of them. We're going to look at axial length at 5 years. We're going to look at the 3 lens types. We're going to look at our descriptive statistics, homogeneity of variance test, and these 2 tests that we'll talk about later. And we'll also do post hoc tests. We'll do LSD. That stands for least significant difference. And the Reg-WEF is kind of a good one for adjusting p-value post hoc. Oops. This is a very common error. I did not turn off the split files. Now, I don't want to turn off all the split files. I just want to get rid of the lens type because that's the group we're testing. So you can't split into different groups, it won't work. Now we want to keep in here because we want to do the analysis twice. Once for the left eye and once for the right eye. Make sure we get it's kind of like a mini replicated study. Okay, so let's look at our descriptives. Now remember, we want to have equal variance. Our test of equal variance, we can look down the standard deviations. They're actually not as far off as I thought they might be. And our test would say the Levine's test after 5 years, really not too bad, really. The right eye is starting to get into the neighborhood. Now, we have sums of squares for between and within. We divide the sums of squares by the degrees of freedom and we get the mean square. Within group sums of squares divided by degrees of freedom, mean square. The ratio of the sums of squares over between groups or the mean square between over mean square within is an f-test. And just looking at the magnitude of the f, the right eye showed a little bit bigger difference. Now, the robust test of equality of means shows that even though it wasn't significant, these statistics are basically equivalent to the F statistic. So you can see that the Brown-Forsythe test, which basically is exactly the same thing as this one, except instead of computing sums of squares by taking each observation and subtracting it from the mean, you subtract it from the median. That's Brown and Forsythe. And Welch, I'm not sure exactly how that does it, but it's a good test if homogeneity of variance is not equal. So if we look here, we can see that the Welch test, which is for homogeneity of variance, the statistic is actually a little bit larger than for the F, because remember it was 0.05 or 0.09 for the homogeneity of variance test. The left eye was the variances, the homogeneity of test variance was not very significant, so that value is closer to the F here than the Welch test for the right eye is to the right eye. They're both significant though. This shows our significant tests. If we look at the left eye, and these are the least significant difference tests, these do not adjust for multiple comparisons. It's like doing a t-test with using the square root of the mean square error as the standard deviation, and then dividing that by the square root of n to get each group to get the standard error. So we can look here, we see for the left eye, we compare the spherical that works well with the spherical that doesn't work, and it's not quite different, but it's close. It's in the neighborhood, 0.075. This is the difference between the means. This is the difference between the means for spherical works well and aspheric. And there is a difference. So if we look up here at our means, we see we have, after 5 years, the shortest axial length are the aspheric eyes, or lenses. Next is the spheric, and next is the spherical, which doesn't work. So these are the longest, and that's what you would expect from that graph that we looked at. So we get a difference, even though they looked pretty close on the plot, the aspheric and spherical works well were different. Then it just does the same thing, but puts spherical doesn't work well. So there's 3 sets of post hoc comparisons, and they basically report the same difference twice. So here's spherical works well, spherical doesn't work. Here's spherical doesn't work with spherical works. So it's the same number, the same difference, 0.379, just the sign changes. Same P. So is aspheric different from spherical doesn't work? Yeah, it's real different. And the right eye, same thing. In this case, spherical and works and doesn't work are significant at 0.04. Here it was 0.07, here's 0.04. That's why, you got to be a little careful when you're talking about p-values that go by a rigid 0.05. Chances are those guys are kind of different. Okay. This is the REGWF test, and the way you interpret this is that it gives the number, and for groups that are in different columns are different. So aspheric is different from spherical works well and spherical doesn't work well. And spherical works well is not significantly different from doesn't work well, because they're in the same column. So you got this guy over here by himself. He's different from these two. These two are not different from each other. As we saw above, they're on the right eye, they're all different. And that's confirmed down here, because aspheric has its own, so that means it's different from these other two. This guy is different from this guy, and so everybody's different for the right eye. And that's basically what you look at for this. Now, if you're going to plot your data, let's open up a spreadsheet. Make that a little smaller. Come in here, minimize, or not minimize, but make that a little smaller. Now we can see both of these on the same page. Let's copy the means over. So we have our descriptives. Copy. Let's get some information about the ANOVA. This is also a good way of saving your output. I usually put this output on the same spreadsheet that contains the data. I think that's all we're going to need for now. And let's insert a bar chart. First of all, we want to, we could do this two ways. We could look at all of both left and right side by side, or side by side. Let's see what that looks like. Insert bar graph. So we have the left eye here and we have the right eye here. We would get rid of total because that's kind of misleading a little bit. And the, oh, and this is N also, by the way. So it would look like this for the left and right eye. Or we can just move up and look at these three and then select data, edit this series, click over here on left, say OK, and then add. I'm going to click on the right because we're up here on the right, and our series value is going to be these points right here. Okay. And now we see how our graphs look. Now, there's a couple things about this. OBS now lets you print your graphs in color, so I don't happen to care for these colors, but we'll let that go for now. I'm going to format the data series, and the first thing that pops up is this gap width, which I think is way too big. I'm going to bring it down to the neighborhood of 50%. Makes our bars a little wider. Now, one of the things that would be nice is to add error bars. And we talked about the least square, or the least significance test, LSD, saw what that showed. Let's plot error bars that are equivalent to that. If we just did plus or minus a standard error, that would be 68% confidence intervals, too small. If we did the confidence interval, 95%, those would be too big. The one that's just right turns out to be the 84th% confidence interval, and let's see how we're going to do that. Now, we said before that the square root of the mean square error is the standard deviation. So we can come up here and we can say equals square root of this number. We're going to hit F4 so we make it a stick there. And then we're just going to copy down these first three. This is the left. Now we're going to do the same thing over here. We're going to look at the right eye. We're going to go equals the square root of this value. And did I hit F4? I did not. So F4 fixes that value. I'm going to copy that down. Now, how do we figure the 84th percentile? Because remember, our confidence interval is mean plus or minus the t-value that we're interested in times the standard error. Now this is so far we have the standard deviation. We need to get to the standard error. I guess I should do that first. So that is equals, what's the standard error? It's the standard deviation divided by the square root of n. So there we go, come down here, and those are the standard deviation, or the standard errors. Now we're going to say, okay, let's compute the, if this was a z-test, we would want 1.96, but it's a t-test, and so we're going to look at equals t-inverse, because we're going to give it the probability and have it compute the t-value. And we want the 84th percent interval, so we're going to go point, and it's 1 minus 0.84. So we get the tail rather than the whole body, so it's 0.16. And the degrees of freedom are n minus 1. That's n minus 1. And that's the t-value for these things. So we copy that down. And then we want to find the confidence interval, just the bracket piece. So that's going to be the t times the standard error, 0.19. Now what this is the value of the difference from the mean. And so notice they're not all the same because the n's aren't always the same. The smaller the n, the bigger the interval. Now we want to add confidence intervals, the 84% confidence interval. We want to put these error bars in our graph. So we go to Design, add a chart element, error bars, more error bar options, come down to Custom, specify the value, and we want the positive values and the negative values. Now these are the deviations from the mean. See how it's already put something in here? It's the top and bottom minus the mean. So we want the difference from the mean here. And then we also want it for the negative values. It's the same interval. These are symmetrical. Now if we had done a log transformation, you would have to calculate this interval separately. It gets a little more complicated to do this with the log. So that's our left eye. Now the right eye, we want to add error bars. More error bar options. Over here at Custom, specify the value. It's the positive is this group. The negative is this group. And OK. And now we have error bars. And just to kind of make them a little neater, we'll format them. Actually, we're not going to do that. So you can see now, for example, let's make this a little bit bigger. Notice that this line right here is pretty darn close to there, but this is the works well versus spherical doesn't work well, and those were like 0.04. The blue lines clearly overlap, and the aspheric values clearly do not overlap with the others. So that's what the 84% intervals do. The graph is presented. You not only know the means, but you can tell from significance instantly whether these are out here. This is an unadjusted p-value, p less than 0.05, if they do not overlap. So that's analysis of variance from soup to nuts.